Hello guys, so today we would like to present about the FTIR. Okay, before we start, let me introduce my group members. So we have Ikmal here.
Hi.
Shamim.
Hola.
Amir.
Hi.
And me, Zahir. And do not forget our cameraman, Asif. And
Enjoy this video.
What is FTIR? FTIR stands for the Fourier Transform Infrared, the preferred method of infrared spectroscopy. In infrared spectroscopy, IR radiation is passed through a sample. Some of the infrared radiation is absorbed by the sample and some of it passes through transmitted. The resulting spectrum represents the molecular absorption and transmission, creating a molecular fingerprint of the sample. Like a fingerprint, no two unique molecular structures produce the same infrared spectrum. This makes infrared spectroscopy useful for the several types of the analysis.
theory of FTIR. Why infrared spectroscopy? Infrared spectroscopy has been a workhorse technique for materials analysis in the laboratory for over 70 years. An infrared spectrum represents a fingerprint of a sample with absorption peaks which correspond to the frequencies of vibration between the bonds of the atoms making up the material. Because each different material is a unique combination of atoms, no two compounds produce the exact same infrared spectrum. Therefore, infrared spectroscopy can result in a positive identification, equalitative analysis of every different kind of material. In addition, the size of the peaks in the spectrum is a direct indication of the amount of material present, which modern software algorithm infrared is an excellent food for quantitative analysis.
Why FTIR? Fourier Transform Infrared (FTIR) spectrometry was developed in order to overcome the limitation encountered with the dispersive instrument. The main difficulty was the slow scanning process. A method for measuring all of the infrared frequencies simultaneously, rather than individually, was needed. A solution was developed which employed a very simple optical device called an interferometer. This interferometer produces a unique type of signal which has all of the infrared frequencies encoded into it. The signal can be measured very quickly, usually on the order of 1 second or so. Thus, the time element per sample is reduced to a matter of a few seconds rather than several minutes. Most interferometers employ a beam splitter which takes the incoming infrared beam and divided it into the two optical beams. One beam reflects off of the flat mirror which is fixed in place. The other beam reflects off of a flat mirror which is on a mechanism which allows this mirror to move a very short distance, typically a few millimeters, away from the beam splitter. The two beams reflect off of their respective mirror and are recombined when they meet back at the beam splitter. Because the path that one beam travels is a fixed length and the other is constantly changing as its mirrors move, the signal which exits the interferometer is the result of this beam interfering with each other. The resulting signal is called an interferogram, which has the unique property that every data point, a function of the moving mirror position, which make up the signal has information about every infrared frequencies which comes from the source. This means that as the interferogram is measured, all frequencies are being measured simultaneously. Thus, the use of the interferometer result in extremely fast measurement. Because of the analysis requires a frequency spectrum, a plot of the intensity at each individual frequency in order to make an identification. The measured interferogram signal cannot be interpreted directly. This transformation is performed by the computer, which then presents the user with the desired spectral information for analysis.
The sample analysis process. For the first of all is the source. Infrared energy is emitted from a glowing black body source. This beam passes through an aperture which controls the amount of energy presented to the sample. For the second is the interferometer. The beams enter the interferometer where the spectral encoding takes place. The resulting interferogram signal then exits the interferometer. The beam enters the sample compartment where it is transmitted through or reflected off the surface of the sample depending on the type of analysis being accomplished. This is where specific frequencies of energy which are uniquely characteristic of the sample are absorbed. Fourth, the detector. The beam finally passes to the detector for final measurement. The detector used are specially designed to measure the spatial interferogram signal. For the last process is the computer. The measured signal is digitized and sent to the computer where the Fourier transformation takes place. The final infrared spectrum is then presented to the user for interpretation and any further manipulation.
So, we come to the advantage of the FTIR. Some of the major advantages of FTIR over the dispersive techniques include: first, speed. Because all of the frequencies are measured simultaneously, mass measurement by FTIR are made in a matter of seconds rather than several minutes. Next, sensitivity. Sensitivity is dramatically improved with FTIR for many reasons. The detectors employed are much more sensitive. The optical throughput is much higher, referred to as the Jacquinot advantage, which results in much lower noise level, and the fast scan enable the co-addition of several scans in order to reduce the random measurement noise to any desired level, referred to as signal averaging. Third is mechanical simplicity. The moving mirror in the interferometer is only continuously moving part in the instrument. Thus, there is very possibility of mechanical breakdown. The last advantage of FTIR is internally calibrated. This instrument employs a HE&E laser as an internal wavelength calibration standard, referred to as the corner's advantage. These instruments are self-calibrating and never need to be calibrated by the user.
Okay, that's all from us. Thank you for watching.
Cheers!